Electromagnetics can be divided into various regimes based on wavelengths or frequency of wave. So these regimes include a static or quasi-static regime for very low frequencies, and microwave and radio frequency regimes for intermediate wavelengths, and optical and X-ray regimes for extremely short wavelengths, each with distinct characteristics and applications. So, a particular case of low frequency approximation is used, for instance, for electrical machines and generators and transformers. And when the frequency is low or the wavelength is long, the governing equation for electromagnetic field is a static equation. This either Laplace equation or Poisson equation. Laplace equation is an elliptic equation where solution is smooth without existence of singularities or shocks. And in electrostatics, a common problem is to find a function that describes the electric potential of a given region. If the region does not contain charge, a potential must be a solution to Laplace equation, or so-called harmonic function. So harmonic function is simply a twice continuous differentiable function. The boundary condition in this case are interface condition for electromagnetic field. So if there are no current density in the region, it's also possible to define magnetic scalar potential using similar procedure. And the solution of Laplace equation is non-oscillatory, implying that it cannot be used to encode the special information needed for long-distance communication. Because the solution is smooth, and multi-grid method can be used to accelerate the solution in this regime. And multi-grid method is an algorithm for solving differential equation using a hierarchy of discretization. So the example called multi-resolution method, it's very useful in problems related to multiple scale of behavior of electromagnetic structure. So we can also, dealing with static, the magnetic field and electric field can be decoupled from each other, and in this regime, electromagnetic equation reduced to electrostatic and magnetostatic equation, and they're separate, right? So they decouple from each other. And the equations of electrostatic also govern the working principles of capacitor, and equations of magnetostatics, they govern working principles of inductors. And when the frequency is very low, the current decomposes itself into a divergent-free component and curl-free component. So this is also known as Gauss decomposition, and it can be observed from the equation where we reduce electromagnetic equation and the frequency basically vanish when it's small, when omega tends to 0. So Ampere's law says that current J produces magnetic field H, and since the divergence of the curl H is equal to 0, then it follows that this current is divergence-free. From the continuity equation, we can derive the relation between current J and the charge rho. So this implies that the charge rho that produces the electric field E comes from non-divergent free part of J. And because of this, in the limit when omega is 0, current J decomposes itself into irrotational component, which is J R. So it's curl free, but not divergence free. And we also have this solenoidal component J sol, which is divergence free but not curl free. And these irrotational current models, the quasi-static field, and the solenoidal current models the magnetic quasi-static field. And again, as I mentioned before, it's known as Helmholtz decomposition. So in order for the equation to reduce to finite charge 0, it seems that JRR should be the order of omega when omega tends to 0. So many computational methods of electromagnetics which are developed for the cases when omega is non-zero, they break down, so omega tends to 0. This is because those methods, although capable of capturing the physics of electromagnetic field when omega is non-zero, they fail to capture the physics correctly when omega tends to 0. Okay, so let's discuss a little bit complexity. So the low frequency approximation consists in setting epsilon not equal to 0. So we neglect the displacement current in the equation. And the electrical current density was taken in this form, right? And here the sigma is the electrical conductivity. So the low frequency approximation removes the electromagnetic waves present in the full Maxwell equation and makes it possible to take time steps on a much longer time scale. So this time scale is associated with the penetration of the eddy currents in conductors. However, the low frequency approximation is mathematically more complicated because of regions with sigma equal to 0. So the time derivative of E drops of the equation, and as a consequence, this equation gives no information about nabla E in the non-conductive regions, and so that E itself is not actually known. So low frequency equations are important in the area of electric power engineering and electromagnetic compatibility. But some challenges that frequently occur in eddy current problem come from extremely complicated 3D geometry and thinly of currents caused by the skin effect. So next, let's discuss the mid-frequency regime in electromagnetics. So earlier I showed a Maxwell equation with time variable. So one can Fourier transform Maxwell equation and arrive at frequency domain version of electromagnetic equation. And here, if we consider vacuum, which is source-free region, we have rho equal to 0 and j equal to 0, and then also b equal mu naught h and d equal epsilon naught e. So in this case, the simplest homogeneous solution to the above equation has the form of a exponential I k r, and here a is orthogonal to k, and the absolute value of k is defined as an omega over the square root of mu naught by epsilon naught. So in a plane wave, the concept itself is essential, and we discussed earlier that Maxwell work bridges the gap between optics and electromagnetics, because scientists once thought that electromagnetic phenomena is different from optical phenomena. Also, the electrodynamic problem, last two of the above equation can be derived from the first two with appropriate initial condition. So the last two equation can be ignored for dynamic problem. And the mid-frequency regime is where the electric field and magnetic field are tightly coupled together. So it is also a regime where electromagnetic field become electromagnetic waves because of this tight coupling. So the field, instead of being smooth, as in solutions to Laplace equation, it becomes oscillatory, so which is typical for wave phenomena. And the oscillatory nature of the field can be used to encode information, and this information can travel uncorrupted over long distances, such as across galaxies. And hence, electromagnetic waves are extremely important for long distance communication. So, in the mid-frequency regime, electromagnetic field can be described by hyperbolic type special differential equation. And if a wave contains broadband signal all the way from static to high frequency, it can propagate singularities such as state discontinuity, which is characteristics of hyperbolic special differential equation. And the oscillatory nature of the field in this regime also prevents methods such as multigrid and wavelength method from being applied in this regime, because the solution is not infinitely smooth.